Welcome students. In today's class, we are going to talk about some more properties of harmonic function. So, properties of harmonic function. Of harmonic function, right? Up till now, we have seen certain properties of harmonic functions, right? I mean, you have, I think you have an idea about these kind of functions. They are very, very special in the sense that I know mean value property. That property is something which only harmonic functions possess, right? So first property which we have seen, and we have seen that this is a very important property, is called a mean value property. Mean value property holds only for harmonic functions, only for harmonic functions, right? This is what we harmonic functions, and this is very important because we have seen that I mean you can prove strong maximum principle out of it, and you also saw that the strong maximum principle holds, right? This also holds. So essentially you see, and to prove strong maximum principle we have again used mean value property. Today we will see more applications of mean value property, and essentially that will give you more properties of harmonic function. So one of the main idea about harmonic functions is, so let's say, see, we did not exactly solve any Laplace equation to find the harmonic functions. We just I mean definitely you see, if Laplacian, let's say if Laplacian u equals to 0, yeah, in some domain omega, of course without solving this thing, you guys already know that u is equals to constant is always a solution. Always a solution. That's always there, right? A solution irrespective of what omega is. Yeah, and of course you can also find a solution which looks like this. It is x square minus y square. That sort of thing will also work, right? This is also harmonic, is also harmonic. Harmonic. And similarly, I mean simple functions, let's say, I mean alpha x plus beta y, that sort of linear functions. So essentially, if you take here alpha beta is in R. So if you take alpha to be 0, uxy is just y, beta times y. And if you take alpha to be 1, beta to be 0, uxy is basically just a x coordinate, right? So essentially what am I trying to say? These are all harmonic functions, and you do not have to worry about where they are harmonic. They are always harmonic, okay? Harmonic. Now, the point is this. So we have already found out three different sort of functions. So this is like a constant function. This is a, I mean, linear function. This is a quadratic one, right? And I mean, you can go on doing this thing. But the thing is, so you do understand there is like a huge variety of harmonic functions. Yeah? Now, the question is this: how does, I mean, without solving this thing, so it is, you do understand that it is definitely not possible to find all possible harmonic functions like this, right? So without solving it, how can we say what are the properties that harmonic functions possess? You understand? An arbitrary harmonic function, not a special one. So the question basically boils down to this. Okay, given an arbitrary harmonic function, and arbitrary harmonic function, okay, what properties can you expect? What properties can one expect? Okay, and it turns out that harmonic functions are very, very special in that sense. Yeah. So because we saw that there is something called the mean value property which holds, and there is something called the strong maximal principle which holds. There are other properties also like this, and we have also saw that there is something called positivity, which is just a application of strong maximal principle. Yeah, that holds for harmonic functions too. Yeah. Today we are going to prove something different. Yeah. A different property. So maybe I can just do it here. Yeah? Maybe I can do it here. So the thing is this. This is very important. It's called a regularity. Okay. What it means is this. See, let me do the motivation over here. Now think of a function. Let's say Laplacian u equals to 0. Yeah. Whatever it is in omega. Let's say. Yeah. 0, what sort of function is this? This is basically a C2 function. You can think, oh, this is a continuous function, right? I mean, you don't worry about all that. It is basically a continuous function. Yeah? So whenever you are solving this problem, you are basically saying that you are looking for, so essentially we are looking for u such that uxx plus uyy equals to 0. Yes. So essentially you are, or you can also think of this like uxx equals to minus uyy, right? Yes. So essentially, you see, if you just look at this property, what it says is you are looking for a function such that the double derivative like this uxx plus uyy, okay, that is 0, which is a continuous function, right? It's a continuous function. So basically, you are looking for a function whose double derivative, the sum of double derivatives, uxx plus uyy, that those two derivatives, if you sum it up, that is a continuous function. So definitely, I mean, without loss of generality, yeah? I mean, we can safely say it's not like it is always going to happen, but we can say that, I mean, we can assume that essentially we are looking for a function such that uxx and uyy are continuous, right? Or continuous. You can safely say that. And such that this happens, such that uxx is equals to minus uyy. Okay, this is what we need to find. Now, if something like this happens, okay, so what does that say about you? That says that at least these two derivatives must exist, the double derivatives must exist, and they are continuous, right? That's what it needs to say. So essentially, you can think of this u to be C2 of omega, right? Yeah, that implies that u has to be C2 of omega. Of course, it may not be C2 of omega. It can be much less than that. But we can safely say that at least u is C2 of omega. And that is where our definition, our motivation of solution is. So let's say if we say that there is a solution to this problem Laplacian u equals to 0, what does that mean? It means that you are basically looking for a C2 function. You are basically looking for a C2 function which satisfies the equation. So maybe I can do it here a little bit. Solution. So let's say Laplacian of u equals to f in omega. Yes. And u equals to, let's say, g on the boundary. Okay. We say, let's say that is your one. We say u in C2 omega is a solution. I will take C2 omega bar, okay? Or I mean, you can also take C2 omega intersection C omega bar, but that's not a problem. I mean, for now, let's just, okay. Maybe we can do it better, huh? Let's do it better. So we say u in C2 omega intersection C omega bar is a solution of one if, so let's take minus Laplacian. Minus Laplacian, there is nothing special about minus, you understand. F can be positive, negative, you can just adjust it here. Huh? If this happens, this is equals to f of x for all x in omega, clear? And u of x equals to g of x for x on the boundary, clear? Okay, so basically you are looking for a C2 function in the interior of the domain omega. So omega, in omega it has to be C2, on the boundary it is continuous. So it is assumed that f and g are continuous functions. Okay, we are just always assuming f and g are continuous. Okay, right. So essentially, you see, whenever we are saying something is a solution, we are always assuming that it is C2 solution. Now, what does regularity say? Regularity is a very important property in PDE study. What it says is this. So it says that is it really a C2 function? I mean, can you comment more on how smooth it is? See, I mean, from intuition, it is very clear, right? That let's say a function which is, let's say, u is in continuous in some interval I, let's assume, yeah? And let us assume that u is C1 in the interval I, okay? Yeah? I mean, vaguely speaking, not very mathematically, but vaguely speaking, just think of the regularity of this. Regularity means, I mean, think of this as a how smooth these functions can be. Okay, so you realize that, I mean, a function which is continuous may look like this, no? Okay, whereas a function which is C1 will never look like this. Okay, so a function which is continuous may look like this, yes, but the function which is C1 will not look like this. Yeah, so you understand that there will be some small, the smoothness is there. Yeah, it will be smooth. It won't suddenly turn around, and I mean, you understand what I'm trying to say. So basically, at every point there are some tangent vectors. Yeah, and now you realize that the more regularity. So let's say a function which is C infinity of omega. Okay, that is very regular, right? So at every point there are tangent vectors, and you can do all sorts of things. So every derivative has tangent vectors and that sort of thing, right? So they are very smooth functions. So essentially the question is this: whenever we say something is a regular, we talk about regularity of PD, we mean that, let's say, that it is in certain space. Huh? Let's say U is in some X. Okay, can that imply that U is in some Y where Y is contained in X? Is it clear? So essentially, what I'm trying to do is this. Let us assume that, I mean, you have, when you are starting to find a solution, you are starting to find it in a bigger set X. Okay, of course. I mean, if you want to find something, I mean, it's better to take the set big and big, so that the chances of getting a solution is much more, right? Okay. Now, once you have found it in a bigger set, now the question is this: is it also in the smaller set? Yeah, the smaller set is the most exclusive set, right? We also want it to be in a smaller set so that it enjoys much more properties. Okay, so essentially, first of all, the idea is this: first you prove it for, you show that the thing is for bigger set, and then you show, I mean, first you show that it holds for a bigger set. Yeah, and then somehow you show that if it works for the bigger set, I mean, does it work for a smaller set also, which is contained in a bigger set? Okay, because you understand, smaller set is much exclusive. Huh? It enjoys much more properties. Okay, so this is the idea of regularity. So what does regularity say? So if U, which is continuous in omega, okay, satisfies the mean value property. Mean value property. Okay, mean value property, you remember, for every ball Bxr contained in omega, then we can say that U is in C infinity of omega. Okay, now what I want you to do is this. Now, for now, okay, just take 5 seconds, then think about what it says. It is saying essentially, so let me explain to you and then just think about it. It is saying that first of all, you start with a continuous function, okay? No C2, nothing. You just start with a continuous function, the biggest set which you can think of, yeah? So you remember this thing, right? Continuous functions in omega is the biggest set, which contains C1 of omega, clear? Which contains C2 of omega, and all of this contains C infinity of omega. So function which is in C infinity is also in all of these sets, right? So note. Okay, so essentially what am I saying is this: you start with a function which is continuous in omega. Okay, now of course not every function which is continuous is in C infinity. I mean, f x equals to mod x is an example, right? That is in C, that is continuous but not in C1, correct? On -1,1 if you take omega to be -1,1. So essentially what am I saying is this: you start with a continuous function such that the mean value property holds. Please remember this thing. This is so important. Whenever we say something is mean value property holds, you guys already know. Once mean value property holds, it's going to be a harmonic function, right? So it says that, and we are not talking about any harmonic function here. We are just saying that you start with a continuous function such that it it satisfies the mean value property. What is the mean value property? Let me again remind you. What is the mean value property? It says that, let's say U at the point x naught, this if you want to evaluate. So basically, let's say given a function, we say that the function satisfies the mean value property. So maybe I can just put it here. Okay. Okay. So essentially, let me write it down. We say that the function satisfies the mean value property if for any x naught in omega, we can write it like this, right? B x naught r u of y d of y, right? Or we can also write it as the boundary x naught r u of z ds of z. right? Where this is the surface measure we say. I mean, if you do not know measure theory, you can just think about it as the integration with respect to the surface, right? Okay. So essentially, just take 5 seconds and think about what this property says. It says that the continuous function with this property, then it will just take it inside this set. You understand? If you skip all that, once it satisfies the mean value property, continuous function will end up in this set. Okay. Just think about it for 5 seconds and we'll come back. What is the mean value property? The mean value property says that if f is continuous in omega, clear? So we start with a continuous function f, yes, and we say that satisfies the mean value property if for any x0 in omega such that you have a small ball which is contained in omega. See, of course, for any x0 you will have something like this. Yes, why? Because omega is an open set and every point is an interior point. So essentially any point you can just put a ball inside omega, right? So you just take any ball. I mean, it does not matter, whatever it is, yeah. Such that there exists R positive for which B of x0 R is contained in omega. We have the value of f at that point x0 is the average of f over B x0 R, yeah, or the average of f over the boundary. Yes. Okay, so that's your mean value property we already know. And the regularity theory says that once you have a u which is continuous in omega, yes, and it satisfies the mean value property for every ball which is contained in omega, then you can show that u is not only continuous but it is infinitely differentiable. That's a huge claim here. Yes. So again, let me emphasize, it is saying that a continuous function with this property is infinitely differentiable. So it's huge property. Okay. How do you prove this thing? So to prove is not very difficult actually. We'll use modifiers to do this thing. So proof. Okay. How do you prove it? So let eta be the radial function which we have proved earlier, the radial function. Okay, and set u epsilon to be, so this is the definition which I am writing here. This is eta epsilon convolution u. Okay, so essentially what am I doing is this. See, you have to show u is in C infinity of omega, right? So you take, you show that u is actually, what we will do is this. We are not going to directly attack u. What we are going to do is we are going to show that you can actually identify u with a C infinity function inside omega. Is it clear? Okay, and what is that C infinity function? That is u epsilon. This is what we need to find. So what we are doing is we are mollifying u, okay, in omega epsilon. Okay, so basically where omega epsilon is the set of all those x in omega such that the distance between x and the bounded ideal omega is greater than epsilon. Okay, so essentially what am I saying? I am saying that omega epsilon, okay, it should be such that it must contain, so essentially let's say that's your omega, yes, and omega epsilon is the domain which is like an epsilon distance from omega. Okay, so this is your omega epsilon. Yeah, what am I saying is first of all I have proved, I will define a set, a function u epsilon which is defined on omega epsilon, right? And that is defined as eta epsilon convolution u. And we say, if you remember, we say u epsilon is the mollifier. Okay, sorry, is the smoothing of u. Okay, so using a mollifier, so you see, you remember eta, we start with a radial function eta and we define eta epsilon as a mollifier, right? Okay, eta epsilon as a modifier, and you see u epsilon is the smoothing of u. So basically u epsilon, if you define it like eta epsilon convolution u, okay, then basically what happens to the u epsilon, you know that u epsilon is a smooth, we say it is a smoothing of u, and essentially u epsilon is, so that or in other words u epsilon is in C infinity omega epsilon. Is this clear? What am I saying? First of all, again, let me explain to you. We are starting out with a radial function. We did it earlier, right? We started out with a radial function. We will always denote it by eta, and we write it and we set this eta is a radial function, which sometimes they call it a modifier, but essentially for now we just call eta epsilon as a modifier. It doesn't matter, but okay. So modifier is what? It actually, let's say you have some problem somewhere, so like sudden bent or something like this, yeah. What eta epsilon does is, when you convolute u with eta epsilon, that particular function which here we are defining at u epsilon, that particular function will be defined in this set, okay, u omega epsilon. It is not defined everywhere, it is defined in omega epsilon, such that this particular function is extremely smooth. It is C infinity. Clear? Now what we will show is, in fact, this u epsilon is equals to u in omega epsilon. Yeah, and since epsilon is arbitrary, it can be as small as you want. Essentially, what we can do is we can show that u epsilon is equals to u. So let's just prove this thing. Yeah. So let x is in omega epsilon, right? Then u epsilon of x, okay, it is the convolution, if you remember. So this u epsilon of x, this we defined, right? So it is eta epsilon of x minus y u of y dy, okay. So that is given by 1 by epsilon power. So this is just, I am just writing what eta epsilon is. Yes, there is nothing special about it. B of x epsilon eta of mod x minus y by epsilon eta of y dy. Clear? This we can do. This is equals to, I can write it like this. So you remember, this is a radial function. Please, sorry, I made a small mistake here. This is u of y. Okay, now this is a radial function eta, and I am integrating it on b of x. And you remember, for any function f, a nice enough function, when you integrate on b of x star, it essentially means that you integrate between 0 to epsilon eta of mod x minus r. So let me write it like this: r by epsilon. I will explain to you what we are doing. Okay, integral del v x star x r u of z ds of z, okay, and d of r. Okay, if you remember, see, essentially what we are doing is, for a integrable function f, integral, if you want to do between this f, yeah, something dz, let's say fz dz, yeah, what we basically can do is, first of all, see, we are integrating between v x not r. So just think of this like, if you want to measure the width of a trunk, a section of a trunk of a big tree, what you do, you just look at one ring. First of all, integrate on one of the ring, and after that extend the ring from 0 to infinity, right? So essentially what am I saying is this, something like this. Let's say I want to integrate in this whole region, yeah, and we center here. What I can do is, first of all, let us look at the value of the function in this particular ball, okay, for an arbitrary ball like this, yeah, which is inside this with the same center. And after that, if I take the radius of the ball from 0 to whatever the radius of this particular thing is, then I can map the whole thing, right? I can span the whole thing. So essentially this will turn out to be 0 to r, yeah, del v x r, you understand, f of something, f ds of s and dr. Yes, okay. maybe I can write it as epsilon. I mean, there is nothing special. Let's write it as epsilon. Yeah, that will be better. Okay. So essentially, what am I doing? I am taking the integral over this. The surface, and after that, I am just extending the surface from 0 to infinity. That will give you the whole volume. Okay. Right. So this is what we are doing. Now you see, where is x? X is in the center. Where is y? Y is on the boundary, right? And what is the distance between x and y? That is basically r. So that is why this r, I can just put r here. Mod x minus y is basically r. Okay. Is it clear? X is in the center. Y is on the boundary, right? Y is on the, so essentially this thing I can write it as bxr, right? And xr, what is r? R is varying between 0 and epsilon. So for every fixed r, okay, what is essentially happening is y is on r. Initially, this is your r. See, think of this. This is your epsilon. This is any arbitrary r. This r varies between 0 and epsilon. So r can be here, r can be here, r can be here. It extends. For a fixed r, this is x, center, and y is here. So x minus y is r. So that is why I just put eta of r by epsilon. And again, integral over this ball, u of z, ds of z, dr. Clear? Okay. That will give you 0 to epsilon. If you remember, what is it? See, for any r, okay, x is on the domain omega, right? Okay, and r is lies between 0 and epsilon. So essentially, del b x lies in omega here, and that is why this is basically from mean value theorem. The value of this is u of x. Clear? So I can write it as u of x. Okay, and this is eta of r by epsilon. Okay, this whole thing is u of x, so I have took it outside, d of r. Clear? Okay. I am missing something. I am missing the value here. So this is n alpha n r power n minus 1 dr, right? That will come if you remember. So this is just the average, right? The average part should be there. Okay. Why? Because you see, del b xr u of z dz, this is the average is there, so that gets multiplied here. So that will be the surface area of the ball, which is n alpha n r power n minus 1. Okay, and what is it? U of x, right? So that is what I'm just putting it here. Yes. Now once I do this, what happens? You can calculate this thing. This will become b0 epsilon. Okay, whatever we did here, we are just reversing it back. Okay, eta epsilon dy. Okay, if you are not convinced, start with this thing. Eta epsilon, you just integrate it. Eta epsilon is a radial function. If you integrate it on b0 epsilon, you will get this thing, right? Okay, so please check this part. Please check this part. This is radial integration of radial function. Okay, from here to here. So integration of radial function. Okay, so this happens, and we already know what is the integral of eta epsilon over a ball. This is 1. So essentially, this actually comes out to be u of x. Clear? So thus, what did we prove? Thus, we prove that u epsilon, okay, is equivalent to u, right? U epsilon of x is equal to ex in omega epsilon. Clear? Therefore, u is c infinity in omega epsilon. Okay, for each epsilon positive. Yes. Why? Because u epsilon, by definition, u epsilon is a mollifier. It's a smoothing of u. So essentially, u epsilon is c infinity of omega epsilon. So if u is equal to u epsilon in omega epsilon, okay, that will give you that u is c infinity in omega epsilon for each epsilon, and hence u is c infinity of omega. Okay, So one small remark which I want to make is this. Note that we are not saying u is C infinity omega bar. Okay, we are not saying that. So basically, it may not be C infinity up to the boundary. Is this clear? What am I saying? It may not be C infinity up to the boundary. What we can say is inside the domain, it is always C infinity. On the boundary, it may not be C infinity. Is this clear? Okay. So please remember this thing. Right. So now what we are going to do is, so essentially what we learned is any function, continuous function satisfying the mean value property is C infinity. Okay. Now we are going to prove an estimate, which is an extremely important estimate. It's called the estimate on derivatives. Okay. So another property, estimate on derivatives. Estimates on derivatives. Okay. What does this say? It says that assume that u is harmonic in omega. Clear? Then the following happens. It's a very, very important property. Okay. Then what happens is d alpha of u of x. Clear? This is less than equals to ck by r power n plus k integral b x naught r mod u. Okay, I mean, of course you can write u of x dx, but anyways, I mean, I don't care. I mean, you can write it if you want. Okay, let's just write it if you want. It's better. I'm not writing all the times d of x and all. Yes, I mean, please understand that. Okay, so essentially, what am I saying is this. Sorry, it has to be x naught. Okay, what am I saying is, from the earlier estimate, what do we know? That any harmonic function, see, a continuous function satisfies the mean value property is basically saying harmonic function. So any harmonic function is C infinity, right? So say u is harmonic in omega, yeah. Then you can take any derivative d alpha of ux naught. Definitely that is true, right? Because it is C infinity. So you take any derivative d alpha of ux naught, and that you can bound it by ck, some constant ck, by r power n plus k. This is very important, and the integral of u over bx naught r. Clear? And this holds for each ball bx naught r which contains in omega. Okay, and for each multi-index alpha such that mod alpha equals to k. If you remember multi-indexes, okay, so those basically are used to write down the derivative. Okay, so for all multiple index up till k, so dk of u, if you just write it like this, dk of u, that is always bounded by the k derivative of u, that is always bounded by ck r power n plus k, the integral of over u, over the ball. Okay. Now, do you think the integral is defined? Of course, it is defined. Why? Because it is a infinity function. It's a smooth function over a ball, right? So the integral is defined. Here, one thing. What is ck? So c naught is very important. This is 1 by alpha n. And what is 1 by alpha n? 1 by alpha n is the, if you remember, this is the volume of the unit ball in Rn. Clear? Is the volume of a unit ball in Rn. And what is ck? Ck is 2 power n plus 1. Okay, it's just some calculation. I mean, you don't need to get intimidated by anything. I will explain to you why all of this is coming and what is so important here. K equals to 1, 2. Okay, so essentially what it is saying is, you see, in PDEs, this is a very important aspect of PDE. So let's say given any PDE, I mean, not any PD, most of the PDs, what you want to do is you need to, let's say, without knowing the solution, what exactly is the solution, we want to know how the solution behaves. Yeah. From here, let us assume that this is true, right? Let us assume that this is true. We did not prove it. Let us assume this is true. If this is true, what can you say? Think about it. What can you say about the behavior? So let's say if you can take the balls as big as possible. Let's say you can take the balls as big as possible, right? Okay. So in RN, if you are working, you can take the balls as big as possible. What can you say about the behavior of D alpha? That it is always bounded by this. So the growth, what it means is the growth of U, yeah, at that point, if you just look at the derivative, the alpha derivative, so this is the kth derivative of U, the growth is always controlled by 1 by r to the power n plus k. Is this clear? Okay, so it depends on the ball, in which ball you are looking at, what is the radius of the ball, and with the radius, there is a direct relation between these two. The growth is always controlled here. That is what it is saying. Okay, so let us prove this thing, and the proof is very easy. Yeah, we will also see a very, very important, I mean, this may not look much, but let me put it this way. Yeah. So this is a star candidate. Let's just put it like this. I mean, here most of the things are very important, but this is a star candidate. Huh? Very, very important. Very, very important. Okay. This estimate. So how do I prove this thing? So essentially, you see, I have to prove it for all k, right? K is a natural number. So the most natural thing to do to prove something like this is to use induction. Yeah. So let's just do it for k equals to 0. So proof. What happens for k equals to 0? If you can, you guys tell me what happens? Just think about it. What happens when k equals to 0? For k equals to 0, mod alpha is 0. If mod alpha is 0, essentially you are looking at only u of x. So if u is harmonic, let's just write it down. If u is harmonic, u of x, how can you write u of x? Yeah. If u is harmonic, u of x can be written as, let's say x naught can be written as integral b x naught r u of z dz, right? That's what we can write it like this. Now, if we can do it like this, and of course, r is such that b x naught of r is contained in omega. We are always assuming that, okay? Yeah. Now, if this happens, then we can say that mod of u x naught, therefore, is less than equals to the volume of this thing, which is 1 by alpha n r power n. Clear? And integral u of z dz over b x naught r, the mod of this. Yeah. So this is, you can of course always write it as 1 by alpha n r power n integral b x naught r mod of u of z dz. I think you guys, all of you guys know, because mod integral of f is always less than equal integral of mod f. Yeah, that is always true. Okay, so if that happens, you see, this is true, right? This is true. Now, if this is true, what is 1 by alpha n? That is defined by c naught. So this is c naught by r power n integral b x naught r mod uz dz, right? Yes. See, this is the same thing which we proved. It is k equals to 0 c0 by r power n, k equals to 0 r power n integral mod u over the ball. So this is what I wrote here. This is what it is. Yeah. So for k equals to 0, it is true. So hence star is true for k equals to 0. Okay. Now, what happens when k equals to 1? Let's just see. Now, for k equals to 1, we have observe this particular thing. Observe. See, if u is harmonic, u has infinite derivatives, right, to work with. So if u is harmonic, observe, if u is harmonic in omega, that implies u of xi is also harmonic in omega for I equals to 1 to n. Is this clear what am I saying? See, what I am saying is this is a very, quirky result. It says that if u is harmonic, if Laplacian u equals to 0, then you can take the derivative of u of xy. If you just think of Laplacian of u of xy, you can show that even that is 0. Okay, so u is harmonic, it means that u of xi is also harmonic. Okay, and therefore, if u of xy is harmonic, u of xy satisfies the mean value property, right? So what you can do is you can write u of xy at the point x naught, that is equals to integral b x naught r by 2 u xi. I don't know, maybe we'll write down dx. Okay, so that is this. Now, if this is true, yeah, so this is mean value property. Yeah, please remember mean value property. I'm using mean value property. Why I can use? Because I have, if u is harmonic, u of xi is also harmonic, right? If u of xy is harmonic, then u of xy also satisfies the mean value property, and that is what I'm using on u of xy, not on u. Okay. So from here, this you take the integration by part. Okay. If you remember your integration by part, this is equals to 2 to the power n by alpha n r power n. Okay, see here I'm just writing it down. I'm just breaking it down. What is the volume of the ball? It is basically alpha n r power n. Here r is r by 2. That is why just this is okay, and that I can just write it down as del b x naught r by 2. Okay, and u gamma I dx. I think it is quite clear how this is coming. This is indication by parts. If you remember Gauss divergence, or you can just write it as Gauss divergence theorem. Yeah, we did this. So integral over the ball of uxi is basically u dot gamma I over the boundary of the ball. Clear? Now, this I can write it as less than equals to 2n by r. Okay, the maximum of mod u over the boundary x naught r by 2. Okay, let's just think about it, how we can do it. See here, if just take the maximum. U is a continuous function, right? Yes, u is a continuous function in omega. I am looking on only, let's say that's your x naught, okay, and this is r by 2. So I'm only looking at this portion of the domain. If u is continuous, definitely, this ball del b x naught r by 2, that is a closed bounded set, right? Hence it is compact, continuous function compact set. There is a maxima. I will take that maxima out. If I take that maxima out, essentially what do I have? 2 to the power n alpha n r power n and integral over del b x naught r by 2. This is gamma I. If I just dominate it, it is basically dominated by 1, right? Gamma I is the unit outward normal, if you remember. Yeah. So gamma I, this is gamma I, yeah? Unit outward normal. So this you guys already know, so I'm just not writing it here. This is d of x. Yeah. Now 2 to the power n alpha n r power n. This is basically the volume of this. So basically the surface area of this thing. What is the surface area of this? It is n alpha n r by 2 whole power n minus 1, right? That's what the surface area of this particular thing is. So if you calculate this thing, there is 2n, alpha n is getting cancelled, right? And you have 2n by r, and the maximum of u is always there. Okay, so this is there. Now, see, if del b x naught r by 2, okay, contains x, let's say this contains x, then the ball b with center x and radius r by 2 is contained in the ball with center x naught and radius r, which is contained in omega. Yes, this is quite clear, because the difference, you see, the difference between x and x naught, the difference between x and x naught, the maximum distance is between r by 2, right? So I can just take a ball with center at x and radius r by 2, which is contained in b x naught r. Yeah, and of course that is contained in omega. Yes. Therefore, what we can say is u of x, yeah, is less than equals to 1 by alpha n 2 by r whole power n, okay, integral module b x naught r, right? So this you can say. Yeah, I hope this is fine. Why we can say this thing? Why we can say this? Because this is the mean value property, right? From mean value property we can say this thing, right? I mean, this is just we prove for k equals to 0. Yeah, for k equals to 0 we just prove. So for k equals to 0, this is what I'm writing. For any x, please remember the difference here is this. Here we prove it for mod u of x naught can be written like this. Okay, what I'm saying is here for any x, yeah, such that bx r by 2, which is contained in bx naught r, we can write it like this. Is this clear? Okay. So once this is true, you combine these two properties, the earlier property, this property, and this property. Once we combine these two, we get mod d alpha of u at the point x naught. Okay, this is less than equal to n plus 1 n by alpha n times 1 by r power n plus 1, okay, u L1 of b x naught r. Clear? Okay. So combine this and this. So for any x such that this happens, u of x can be bounded by this, and so we use this property here. So this is less than, you take the maximum here, the maximum will also be bounded by this. So essentially what am I saying? I am saying that mod u of xi at the point x naught can be bounded by 2n by r times this whole thing, right? And that is why this thing is coming. Okay, so we have proved it for k equals to 1. Now what you need to do is you need to prove it for an arbitrary, k, let's say m equals to 1 I have proved, m equals to 0 by mean value property, m equals to 1 we proved. Now we'll just have to show for m equals to an arbitrary k, let's say. Yeah, and this thing is exactly the same thing, whatever we did earlier. Okay, whatever the exact idea, whatever we did for k equals to 1, the exact idea will work. Okay, so I'm going to skip this part. So for an arbitrary n equals to arbitrary k, the above logic can be modified. Logic can be modified, okay, to achieve the required result. Is this clear? Okay. So for an arbitrary k, I mean, we are doing induction, right? For an arbitrary k, you just think of it like it holds for k minus 1 and do it for k. What you need to do is exactly whatever we did for k equals to 1. The exact same sort of thing will work. Huh? You just have to change things a little bit. Okay. But this is for yourself. So please check this part. Huh? I'm not going to do this. Okay. This is not very difficult. The same kind of thing, and you should be able to do this thing. Yeah. Okay. Now we show another property of harmonic function. This is a very important property, and I am quite sure all of you guys already know this property. This is called the Liouville's theorem. Okay. So from complex analysis, you guys know that if a function is a holomorphic function, then the real and imaginary part are harmonic, right? And you can show that there's a Liouville theorem in complex analysis which says that bounded entire functions are constant. Yeah. So it's exactly the same thing, but only in the real case. Okay. So what we are going to show that there is no non-trivial bounded harmonic function in whole of Rn. Okay. So let u from Rn to R is harmonic. Okay, and bounded. Is this clear? So I am starting with a bounded function which is harmonic and Rn. Okay. Then U is constant. Okay. So quite clear. Okay. How do I show this? So for the proof, what I do is you fix x naught in Rn, and R positive. Clear? Okay. Right. Once you do that, can you say something like this? du at the point x naught. Let's just look at this thing. Yeah. This is less than equals to root n c1 by r to the power n plus 1 integral mod u over b x naught r. Yeah. Can I say this? If you remember, you see the derivative of u at the point x naught can always be bounded by this particular thing, right? Yeah. So that is what I am writing here. So essentially, you see, this is always bounded by some constant times 1 by r to the power n plus 1, the integral of u over ball. Okay. So this is actually, okay, one thing I want to clarify. Whenever I am writing some function, the L1 norm of some function, essentially this is a shorthand of writing this. Clear? This is just a shorthand. Okay. Okay. So I'm just getting it from the earlier. So from the earlier theorem, we know that d of u x naught can be written like this, right? Okay. Now you see, this actually says everything here. Once you do this thing, you can just write it. I mean, if you just u on the ball, yeah, it has a maxima on the ball. I mean, you can take a maxima on the ball. You can just see u is bounded in whole of Rn, right? Okay. So the maxima of u in the whole of Rn exists. So essentially what I can do is I can do this. I can write it as root n c1 alpha n by r. I will explain to you why I can write it like this. Maximum of mod u in Rn. Okay, first thing first. Let's understand how we can write all of this. X naught r mod of u dy x, let's say. Yeah. This, first of all, see, you are evaluating u on this ball. Yeah. I can always dominate this thing with the maximum of u over Rn, right? Here I know that u is bounded in Rn. So I am just taking that bound here. Yeah. Maximum, the upper bound. And then I am left out with d of x over b x naught r. Yes. And this is what? It is maximum of, sorry, this is module, maximum of module over Rn. See, here, what is the integral over the ball of d of x? 1, basically. Integral of 1 over the ball. So it is basically the volume of the ball. So this is alpha n r power n, right? That is what? This is equals to this. Okay. I'm just putting it here. That is why that r power n is gone. Okay. And alpha n is getting carried here. So this is how this is coming. I hope this is very clear here. Okay. Now, please understand this thing, that I can say that this particular thing, this term goes to 0 as r goes to infinity, right? See, here I do not have any restriction. This ball, this is our whole Rn, right? Whole Rn, that's the x naught. I'm taking a ball with radius r, okay? With radius r, and in that ball this is happening. The gradient is always dominated by this. Yeah. Now you see, this is always fixed number. I can't change this number. Yeah. All of this is fixed. This is constant. The only thing which can vary is r, because I can take r as big as possible. This, I am working in the whole Rn, right? Yeah. And this bound is independent of r. This bound is on Rn. I am working on whole Rn. I can take r as big as possible, right? So if you take r towards infinity, all of this is constant basically, and what is going to happen? This will go to 0. So essentially, what is happening is in Rn, okay, in the whole space, the gradient of u is going to be 0. So the gradient of u, okay, is identically equals to 0. Why? Since x0 is arbitrary. Right? Since x0 is arbitrary, see, x0 is nothing special is there about x0, right? I mean, you can choose any x0 and you can choose as bigger ball as possible will be centered at x0, no problem. So essentially, that is saying that gradient of u is 0. Gradient of u is basically d of u. Okay? We are always using this notation, right? It is d of u. D of 1 u essentially, yeah? Okay. So gradient of u is 0. What happens if gradient of u is 0? It means u is constant. It means u is constant. Okay, and we are done. So you see, this is the Liouville property, your already known Liouville property, and this is proved in such a easy way. Okay, so what it is saying essentially, so that's a small remark. Let me put this in the small remark and we'll end it here. So basically it is saying that no non-trivial, okay, bounded harmonic function exists in Rn. So the important thing is bounded harmonic function. There are obviously unbounded harmonic functions in Rn, but there is no non-trivial. So basically it can be constant, but no non-trivial bounded harmonic function in the whole of Rn. Okay. So with this we are going to end this lecture.